Hello. In this video, we are going to look at systems of nonlinear inequalities. So nonlinear, that means that one or both of the inequalities that we are dealing with is not going to be linear. In this case, we have something that is quadratic or a parabola and then a line. And then inequalities, that just refers to the fact that instead of an equal sign, we have an unequal sign, rather a greater than or equal to, as well as a greater than. So we want to solve this system. We want to graph that in a Cartesian plane, and then we want to find the coordinates, the ordered pairs, for the points of intersection of each of these two graphs. So now a couple of things we want to think about. One thing is that if our inequality symbol is greater than or equal to, as well as less than or equal to, when we graph that, we need to make sure that we will have a solid line. Also, if we have just greater than or just less than, we will make sure that we graph that with a dashed line. All right, a dashed or a dotted line. And that option, you can toggle between solid versus dashed when you're graphing in the computer program, when you're doing your homework online. Drawing this on paper, you would just need to make sure you draw that as a dashed line. So that goes back to stuff that we learned in algebra before we took this trig class, just making sure that we know how to graph inequalities. Okay, so greater than or equal to means we can be touching solid line. Just a greater than means we can go right up to that boundary but never touch it, and we indicate that with a dashed line. So now let's look at creating these two graphs as well as finding the points where this parabola intersects with this line. When we think about graphing, it's better for us to consider this as a equation. So if we want to graph the parabola y equals x squared, and we should all recognize that that is a parabola. It's our parent function for a parabola, so it's a parabola opening up with a vertex at the origin, which looks like this. Now notice, because this has an equal to, I'm going to graph that with a solid line. For my other inequality, that's the same as y minus 2 equals x, or rather y equals x plus 2. So this is the graph of a line with a slope of positive 1 and a y-intercept of positive 2. So that line is going to be traveling through these dots. And since this does not have an equal to, we need to make sure that when we graph this, we use a dashed or a dotted line to indicate that we can never touch this boundary. So here is our system, both graphed on the same plane. And now we need to decide where to shade. So we have infinite choices that we can choose to determine where to shade. We can choose any point that is not on the line. I prefer to choose the same point both times and to just check each ordered pair in both of the inequalities. You can choose any ordered pair you want. I try to stick with something like the origin 0, 0, or maybe the point 1, 1. Now in this situation, if I choose the origin, that's going to be problematic because the origin is already a point on my line, and we know that's going to give us a true statement. So choose any point you want, any, just not on the line. So in this situation, when I look to check, I'm personally choosing to test the point 1, 0. So that's easy to deal with ordered pair, which is not on either of my two curves. So let's test each equation, or inequality, I should say, each of these inequalities with that point 1, 0. So we've got y greater than or equal to x squared. And that's the same as writing 0 is greater than or equal to 1 squared. 0 is greater than or equal to 1. That is a false statement. And what that indicates is that this point, 1, 0 over here, does not give me a true statement. So that point is on the outside of the parabola. That means we would need to be shading on the inside of our parabola. Anywhere internally on our parabola would give us a true statement. Now, I'm going to erase that shading I just did so my graph doesn't look too messy here. But I want you to keep in mind that outside the parabola, the 0.10 over here was on the, in my idea, outside of the parabola. So we would want to be shading inside the parabola. So I'm going to do my end shading here in a second, but we know for the parabola we're shading inside. So now let's look at that same point with my linear inequality. My linear inequality is 1 minus 2 is greater than x. And if I plug my 1, 0 in, that is 0 for y minus 2 is greater than 1 for x, or rather negative 2 is greater than 1. Again, that is a false statement. This point, which is in a sense, below and to the right of that dotted line, that is not a true statement. That means I need to shade on the other side of the line, which would be up here. So where is above the line and inside the parabola at the same time? Where is this blue shaded region and red shaded region? Where are they overlapping? So inside the parabola and above or to the left, however you view it, in regard to that dashed line, is going to be this region. And you guys, when you're working on your homework online, you have the option to choose the paint bucket, and you just paint bucket only one region. There's only one region that represents our solution set. And so here's a nicer drawn out picture of what this graph might look like in your homework. So you would choose the parabola option to graph a parabola, make sure that it's a solid line. You would choose the line option to grab a line, and then you would toggle to make it look dashed. And then you choose the paint bucket to shade only in the one region where both of my shades are overlapping. So that means that if I choose any point in this yellow region or on the boundary of this parabola, but not on this line, anywhere in the yellow or on the solid line, that ordered pair would be true in both of these inequalities simultaneously. So it'd be true in both of these at the same time. All right, the last thing we need to do is find these 2 points of intersection. That's pretty easy for us to see what they are because in this situation, my line passed through some of the 2 ordered pairs that I was graphing for my parabola. So we can visually see that those points of intersection are going to be at -1, +1, and +2, 4. But how would we find those points of intersection algebraically? Because you can't always just look at the graph and tell. And the way we would do that would be, again, to treat these 2 inequalities as though they are equations. Here I have y equals x squared, my related equation, and y minus 2 equals x, my other related equation. Well, since we know that y is equal to x squared, I can sub that right in, and that gives me x squared minus 2 equals x. At this point, we need to solve a quadratic equation to find the 2 x values which represent our points of intersection. So putting this into standard form or descending order equal to 0, I have x squared minus x minus 2 equals 0. I can factor this. That would be x minus 2, x plus 1 equals 0. And we can easily see that we're going to have x equals +2 or -1. X equals -1 right here, x equals +2 right there. Now, we're asked to write these as coordinates, or points of intersection. So we need these as ordered pairs. Well, since y is equal to x squared, if I plug 2 in, I would have y equals 2 squared, which gives me y equals 4, as well as plugging in -1, that would be y equals -1 using your parentheses squared, which gives me y equals +1. So my two ordered pairs would be 2, 4, or -1, 1. So those are my 2 points of intersection, or as you may call in a later class, those are your 2 vertices, the 2 points where these lines are intersecting. So that is how we deal with a system of linear inequalities, creating the graph as well as finding these 2 points where the line and the parabola intersect. As always, email me if you have any comments, questions, concerns. Good luck.